This program is a presentation of UCTV for educational and non-commercial use only.
Just to sort of to give us a quick idea of where computing is going, although the current sort of energy consumption of computing devices is in sort of the 2 to 5% range if you take everything together, the key is that the energy consumption of these large data centers and computing devices in general is increasing exponentially. And in fact, that's what we want, because we want computing to pervade all the different sectors and increase energy efficiency. Just another perspective on this, I think an environmental group looked at server carbon production and equated it to about an SUV. And so if you take that and you combine that with the sort of exponential growth of computing, this is a serious problem for us to think about. And in particular, computing is in fact the fastest growing segment of carbon production in the various technologies that we look at. So I represent an effort that is probably one of the most diverse groups in the Institute, which ranges from large-scale computing, data centers, even work in buildings, all the way down to sensors and embedded systems, and how that relates, how all these things relate to economic policy and the environment. And as a result, this group of about 20 or more faculty has strong relationships to other groups in the Institute, notably the Buildings Group, which you'll hear from, Silicon Photonics, which you'll hear from, and Electronics, and also the Economics and Policy Center. Just to give you a sense of what we're shooting for here, the idea is that we see that computing is becoming pervasive and increasing exponentially, but we want to sustain that, right? And in order to sustain that, we sort of have our own version of this more than Moore's law, which is that we want to have exponential gains in energy efficiency, both sort of at a technological level and at a system level. And that is how we're going to sustain this growth into the other sectors. And for our center in particular, we have some of these immediate goals of several orders of magnitude improvement in both computation and in critical issues such as cooling technologies. And I'll just break that down a little bit into some of our specific efforts. A short-term effort that we have is to look at basically changing the way that we do computation. Right? Luis Barroso is going to give, I think in his talk, some very interesting results in how well Google has done in making their data centers very efficient. But really the remaining gains that we'll see are in how do we actually do the computation on those servers and computational devices once we've made those systems efficient. And we have at UCSB a lot of expertise in large-scale databases, operating systems, virtualization, protocols, and networking, and server architecture design. And our initial effort is really actually inspired by Google and things that Luis will talk about. And we're looking at how to build systems that will scale their energy consumption with the work that you give them. And it's something that you'll hear more about, which is energy proportionality. Another strength of UCSB is in technologies and materials, which you'll hear a lot about. And one of the other goals of our center is to take those technologies and devices and to sort of fundamentally change the way computational devices are built. And here we're looking at leveraging things such as silicon photonics, such as nanoscale devices, which we have in the California Nanoscience Institute. Just as a simple example, we're looking at using silicon photonics to build very powerful sort of data communication and data sort of permutation or rearranging kinds of devices, which will sort of change the efficiency of difficult computations, such as sparse or irregular sparse matrix kinds of computations, be able to transform those in an efficient way into much easier dense computations. And finally, we have a fairly close tie to the buildings sort of energy or dynamics group that you'll hear from in looking at how to make cooling much more efficient in data centers, in particular looking at novel methods of managing airflow, in looking at new technologies such as liquid or vapor cooling technologies, and integrating those technologies with how we do computation, sort of co-scheduling how we do the cooling with how we do where we put the computation. Another theme here, I think, is that you'll see when you hear from the buildings group is that a data center is a building which is really sort of a nice controlled prototype of some of the building technologies that we'd like to see in buildings in general. And so our efforts here are really to build instrumentation and experimental infrastructure that allows us to sort of prototype some of the things that we'd like to see in new buildings. And I think as a theme in general, all of these technologies that we look at, we'd like to see sort of percolate from sort of the data center level down to commodity PCs, down to embedded systems, into the sort of the whole computing, pervasive computing model that we'd like to see. Okay, so we have two very distinguished speakers in this session. Luis Barroso from Google, who will talk about large-scale data centers. And we also have Feng Zhao, who's from Microsoft, who will sort of, I think, tie together not only work in large-scale data centers, but all the way down to embedded systems.
I want to talk more specifically about things I understand better, which is the kind of infrastructure that's used to build large-scale internet services, the impact they have on energy, what kinds of things they work very well for, and what are the main opportunities we have today, both in terms of best practices as well as what are the areas where new technology can really help. So first, I want to introduce, or at least confess my ignorance on sort of the kinds of terminologies that are around in this area. If you go to this page at Google, I think it's called Google Insights for Search, you can actually look at the relative popularity of different search terms. And as you can see there, over time, grid computing is falling out of fashion, and I guess cloud computing is probably the word that everybody talks about, even though I think most people will confess they don't know what it means, and I'm among them. So I will try explicitly to avoid using that terminology. Sadly, though, utility computing never really took off, as you can see, sort of down at the bottom, because that's probably the one I understood what it meant best. A couple of years ago, I was walking around between a couple of Google buildings in Mountain View, and I saw this. Now, this is not photoshopped. This is a manhole cover that has Google written on it. So this is the first insight I had into what this might actually mean. So instead of talking about these kinds of terminologies, I just want to set up some background. The way I guess many of us at Google look at how computing is evolving is sort of in this direction, in that we're more and more interested in these two sort of ends of the computing spectrum. One of them are very small devices, things like your cell phones, things like the netbooks that Justin was talking about, and then things that look like big warehouses filled with computers. And at Google, we like to use the term warehouse scale computing, and that's a building with tens or hundreds of thousands of machines in there. And this is the infrastructure that's powering many of the internet services that I guess you use today, not just from Google, I guess, but from many other people. So it's interesting that these are the kinds of things that we're migrating towards. And when you look at these two ends of the spectrum, as we'll see a little bit later, the kinds of solutions, especially for energy efficiency, but for design in general, may actually be different when you're talking about one device versus the other. So what I want to do today is breeze through the first part of my talk that's been covered very well by Justin and then by Fred here just as well, in terms of setting out sort of the big picture in terms of where computing is in the energy budget for the planet, for example. I don't think I need to spend much time on that. I want to talk a little bit more of something that only now is becoming a little bit more of a popular theme, which is the energy-related costs of computing. And I'll go a little bit more into detail on that. But I want to spend most of my time at sort of the bottom here, which are what are the efficiency opportunities we see today from where we stand. And hopefully, some of these things will be new to you. So the study that Justin mentioned, Smart 2020, gives you sort of a framework for where computing is. Clearly, if you look at computing as a whole, we are in the small percentage points of the planet's sort of budget, both in terms of emissions and in terms of the electricity budget. It is growing very rapidly, so that's something that we can't ignore, and it's at the level that we can't, it's not negligible anymore. So in this study, they predict that by 2020, the carbon footprint of all of computing, and not just servers, and we're talking about everything here, could grow up by another factor of 2 or so from where it is today. So it's clearly something we have to worry about. So the good news, as Justin sort of alluded to from that same study, is that computing actually helps in a lot of other ways. In the LED lighting talk, you saw a hint for that as well, or the set of talks, in how information technology actually can help you sort of make better use of resources and how you deploy them. So in this study, they estimate that even though computing's footprint may grow a lot, the continuing application of computing technology across many other industry segments can actually more than pay multiple times for its actually growth. There's no reason for us not to worry about its footprint, but it's certainly something that puts things in perspective. Now, what's more interesting from where we stand is how do internet services and the kind of computing infrastructure that is used for internet services fits into this whole picture. And it's interesting to see, and then this slide gives you just an idea of it. And here we're looking at grams of carbon and doing sort of extrapolations, how this server-side computing model can be incredibly efficient for some kinds of applications. In this case, is search. In our best estimates, a regular Google search will consume about a kilojoule or so, right? And most of us here, or many of us here at least, are adult males, and we're consuming about 8,000 kilojoules per day, just to put that in perspective. So, and this includes not just the query itself, but all the work that's done in the background to fetch the data and index there and get it ready for it to be searched. So for some kinds of applications, this model of server-side computing and internet services is incredibly efficient. Another example I want to bring to you is something that's actually been released relatively recently. And that is something that I think is incredibly important for humanity in general, which is us being able to sort of understand people who don't speak our languages. And statistical machine translation is a technology that Google's been using for a while and has been very successful in terms of allowing computers to automatically translate between languages by just essentially using statistical methods, not knowing much about linguistics at all. It's a really interesting field. Now, one of the characteristics of these things, and what's in the past 5 years or so, I think researchers at Google and elsewhere have been sort of great strides in this area, is that these models work well when the language models are incredibly large. So these are things that, and you can see that as we grow the database of language phrases and translation pairs that we have powering these kinds of translation engines, the accuracy of the translations goes up tremendously. So this is clearly another example of one of these applications that will never work very well on a laptop computer or on a cell phone because both the data involved in it is sort of too large for those devices, and the computation that's involved in generating these translations is also enormous. Now, if these services are actually centralized in a few data centers somewhere else, and the whole world sort of can take advantage of that, it's clearly a very effective way of delivering that. In this example, in case it wasn't clear, that's an email I received in Portuguese. And if you use Gmail today and you get an email on a language that's not your default language browser, we're going to give you these links that are shown there that can translate that conversation to some other language, which these days might probably help you more in translating a lot of spam you get in sort of different language than you're familiar with. But for some of us who exchange email in multiple languages, this is sort of an amusing and interesting thing to look at. You can also look at search results at Google these days, for example. And it's particularly useful for non-English speakers. We can automatically translate when we show a page of search results. If your best result is in German, as it turns out, you can automatically translate that page by just clicking on the button that result. The kind of computation involved in that is clearly amenable to these large data centers, and it's much more efficient from a CapEx and from an energy budget as well to run it that way. Now, let me switch gears then and talk about more specifically about how energy has become an increasing factor in the cost of computing. And to set the stage, this is a picture of a Google data center, I think just before I arrived. And at that time, we bought some co-location space in this particular facility, which I think was in Santa Clara. And in this facility, back then, many of you might recall, they sold data center or hosting space by the square footage, right? And what that meant is that the amount of energy that computers could draw on a room like that, or how much they could heat up that room, was actually not an issue. It's really floor space was what determined cost, right? Well, Google being a very frugal company, of course, they gave us so much square footage inside a cage, and we completely packed it in with equipment. And very soon, we had to deploy some sort of auxiliary cooling technology in the form of floor fans, as you could see. And soon afterwards, you stop hearing about people talking about data center space, if you will, resources by the square footage. And today, we talk about that by the watt, right? Essentially, that's what it means. And the reason is the following. If you take a data center and you build a data center from scratch that's sort of 10 megawatts and has, 100,000 square foot of floor space, and you double that floor space, and then you see how that affected the final cost of the data center versus doubling the power capacity of that data center. The latter will have a huge influence on cost, and the former will have a relatively modest one. So data centers are priced by the watts, not by their square footage. So we hear a lot these days about the fact that the cost of energy, of powering a machine, for example, or a server in particular, is higher these days over its lifetime than the cost of hardware itself. I think many of us may have heard this. Now, the more I look at this, I can't find that to be true at all, right? And in this case, I made sort of a spreadsheet extrapolation using just data available on the web. This is not actually from Google's data centers. But if you go to the Dell website and you buy a modern computer there, Dell has a very nice power calculator as well. They'll tell you how much power that computer is going to consume. And you look at what costs to build a data center by the watt, and there's a bunch of sources of information about that there. You put together a picture that sort of looks like that, in that if you look at only these three components of total cost of ownership, the cost of buying hardware itself, machine, servers, storage, et cetera, and that's in the green and the red part. The power bill, what you pay, PG&E or Southern California Edison, I guess in this case, and then the cost of the facility. This is roughly how it breaks down. Right? So it's very difficult to imagine a situation these days where the power cost, your monthly power bill itself, becomes dominant. Now, if you believe what I said before, in that if you look at costs of energy more broadly than that, the facility itself is an energy-related cost because we sell that by the watt. Now, in that case, the costs we're talking about begin to be sort of closer to half of that pie chart, right? So that today, from a cost standpoint, is the most compelling motivation for building energy-efficient data centers. is because when you add all of these energy-related costs, then it's really significant already today. And clearly, the electricity part, tends to grow as well. And as computers get faster, and unfortunately haven't been getting energy efficient sort of necessarily as fast as we want them to completely offset those changes in performance. And I'll talk a little bit more about that. So let me talk briefly about sort of the landscape of things that are available for us to reduce that energy cost, or all those energy-related costs. And I divide them in these two broad categories. One of them is, what can we do with technology that exists already today that we can just do better at? And there's a bag of tricks there, and I'm going to talk about a few of them. And then sort of towards the end are things that we really need new technology from a software standpoint and hardware standpoint. Now that relates a lot to the work that the center that Fred Chong leads is tackling as well. I want to go first over sort of the best practices side of things, because it also relates back to some of the things Justin was saying. One of the things we can do is reduce the amount of energy used in data centers by reducing the unnecessary energy conversions, right? And the example in distributing power to machines inside a data center. And the example that Justin gave you was, using mostly DC data centers and with DC distributions and using sort of fewer transformation steps along the way. We actually took a slightly different approach to achieve sort of the same objective. And what I'm illustrating here is a Google server that we deployed around 2005 or so, where we were able to completely eliminate the UPS room in a data center. For those of you who don't know, the UPS room is essentially a room full of batteries, right? And typically, it's responsible for somewhere between 6 and 10% of energy loss in a data center, not to mention the capital expenses to keep that room there. And that room is there essentially for your data center to be up for 20 seconds, or maybe 30 seconds or so, between the time that the grid goes down and your big diesel generator kicks in the parking lot, right? That's all that room is doing for us. Now, what we did for that server is we got rid of that room, and we actually put a little, relatively inexpensive 12-volt battery at every server. Now, at doing that, we did two things with these servers. One of them is that the cost of that UPS bridge was actually very reduced, because this is actually a volume part that we bought there. The other thing that happened was that we avoided an extra AC to DC and back conversion that's required to use a UPS. So we reduced the energy conversion losses in the data center. A different way to achieve that same goal. Another thing that's sort of, again, in the best practice, I want to also re-emphasize here that there's no crazy new technology here. It's sort of a clever approach, I will admit, happily, since it was my team at that time who was responsible for these designs. I have personally nothing to do with them, but I have bright people working on them. But no crazy technology there, right? Many laptops have architectures that actually look a little bit like that, maybe not exactly. Right? The other thing you can do is be very careful about airflow and the cooling infrastructure. In this case, I'm showing you a sketch of a container full of computers that we deployed again around the same time in 2005. And in this case, that's a regular 40-foot shipping container that we retrofitted to put about sort of 1,000 or so machines inside them. And we engineered that to be just a very efficient computer room in which cold air didn't mix with warm air, and temperature gradients between boards that are at different heights were about the same. We managed also, because of that, to run the whole room, if you will, if you want to call that room, a little bit warmer. And with that, we got a lot of efficiencies as well, because we didn't need to use as much energy in the cooling system in order to keep these running. The other thing that this type of architecture allowed us to do is not use chillers, which are sort of compressor-like things that are very energy inefficient. We use mainly evaporation-based units that allows us to have, to also sort of do a little bit better. That's a picture of a data center that we built using that architecture, again, around 2005 or so. Now, what does that mean? Well, Justin mentioned earlier today this embarrassing situation, which unfortunately I think is still sort of typical for data centers, in that for every watt of energy that enters the building, maybe only half of that ends up going to IT equipment, to servers and networks and storage. And half of them sort of gets lost to cooling and to power distribution, lighting, sort of the other types of loads. And the data center industry has a very simple and very effective metric to judge the efficiency of data centers. It's called PUE, power usage efficiency. And what that means is essentially that. You divide the total amount of energy entering a building by the total amount of energy that's actually consumed by things doing work for you, like computers. And that's the factor of 2 you talked about. And in this case, so the blue part here is the computing part. For every 1 watt used here, you have about 0.7 watts used wasted in the cooling infrastructure for this data center. Another 0.22 watts that are losses in power distribution and conversion along the way, and then maybe sort of about 0.08 watts for other lighting and other loads. Now, again, without sort of crazy technology, the kinds of things I showed you earlier from a data center design and server design space allowed us to get to PUEs not of a factor of 2, but about 1.16 in this particular Google data center. And so you went from a chart like that to another one like that. So losses in a data center were reduced, in this case, by a factor of 6 with respect to what's generally considered industry norm. So it's very impressive. But again, a lot of attention to detail, a lot of good engineering, nothing particularly earth-shattering in terms of technology, right? And we disclosed actually about a month and a half ago in a summit we hosted at Google, and you can find that online if you just search on Google or your favorite search engine for efficient data centers or efficient data center summit, and you find a whole day of videos in which we go into a lot of detail on how this gets achieved. So now, a few interesting implications from this. I mean, when you are in a situation like the one here on the left-hand side, clearly working on non-computing things is very, very important, right? Because half of your energy budget is going there. Now, once you reach that, which I'll claim can be done with technology we know today, then you really need to focus on that big one, right? You really need to just recommit to making electronics and computers, and that includes software and everything else, work much better, right? That's the part of the equation you need to reduce. And for that, the last thing I want to talk about today refers to the energy proportionality issue that Fred just alluded to. Thank you. And from an observation that data centers themselves are different than mobile devices in ways. And it's unfortunate because a lot of the low power technology that's available today in circuits was developed for the mobile world. It wasn't developed for data centers. It turns out that some of it actually applies, some of it doesn't really translate as well. And this is one of them. These devices, by the way, handhelds, hopefully if this talk is interesting at all, your devices are sleeping right now, right? Therefore, the technology behind them is such that when they are in this kind of sleep mode, they're consuming almost no energy, right? Which is very good. And then when you're actually using them, you need responsiveness from these devices because that's one of the main qualities of performance from them. So you want them to be efficient also in the small periods of time where they're using them. Data centers instead, if you look at lots of machines over a long period of time, are rarely at these two extremes of the usage spectrum. And this is a graph of like over 5,000 machines in one particular Google data center over 6 months, and we're averaging their CPU activity levels. And as you can see that as a group, those machines are rarely sort of running at full blast. They're actually relatively rarely, you can see that as well from this graph, completely idle like your cell phones are right now. And instead, they're spending a lot of their time in this middle range here. 20, 30% of their sort of full performance. Now, that's unfortunate for the following reason. The servers that are running there are very, very poor in terms of efficiency in that 30 percentile sort of range. So what I'm showing you here is a graph in red of a very efficient server today that's idling at somewhat 50% of its peak power. And you see how embarrassing this is. A machine that's actually doing no work for you whatsoever, but just happens to be not sleeping, is consuming half of the power of that same machine working as hard as it could for you. Any server you got on the marketplace today is sort of actually a little bit worse than that. That idle power is probably closer to 60, 65% or so, if not more. What happens then is that if you're actually not doing a lot of work, the green curve is your energy efficiency curve for that machine. It's pretty depressing, right? In the 30th percentile range, which is where these big data centers are running all the time, that machine is actually half as efficient as it was at peak. Right? It's also sad because a lot of the benchmarks that we have measure energy efficiency at peak, right? And guess what? We're never there. Now, so here's this energy proportionality argument. It's ridiculously simple. It's almost embarrassing. But unlike handhelds and netbooks and all that, we need machines to work well also in that middle range. Right? And across the activity range, we want them to be very energy efficient. We know how to do the no work, no power. We're getting better at knowing what to do with lots of work, some power, and that middle range is sort of unfortunate, right? We want computers to have a very wide activity range. We want them to go from, working at 1% of their peak activity levels and consuming about 1% of their power to 30 to 40, and sort of, in a way, that's more sort of proportional, I guess, in some way, to the energy that it actually uses. Now, the inspiration I like to give people for that is that machines like that have been built before, right? In this case, this is from a physiology book that I borrowed. And it tells you, for some arbitrary categories that this particular book used, how much energy an adult male expends in different kinds of activities, right? And as you can see that we sleep at about 65, 75 watts or so. But if we're axe chopping, we're really cranking there, like the sort of 1.5 kilowatts or so, and sort of everything in between. So this is clearly a machine that has sort of energy proportionality characteristics to them, and probably for good reasons. We need to build machines that actually have that behavior as well. And if we do, the potential is actually quite significant. And this is a study we did about a couple of years ago and published in the Computer Architecture Conference that said that had Google had machines with this kind of energy proportional behavior, our data centers could actually be using half the energy they use today. And actually, their peak power would go down too for other sort of interesting reasons. We get there by designing better components, and we get there by designing better software that can sort of better manage components that are not necessarily energy proportional. And I won't go into much detail about this, but this is something that can be achieved if we actually put some focus on it, both on the hardware and the software side of the equation. I will mention that Intel and the processor companies actually are doing better at this than the memory guys and the disks and the networks, for example, in general, which is sort of interesting. When you think about computer energy consumption, the first thing you think about is the CPU because it has a big heat sink sitting there somewhere. The CPU is actually has a long way to go still, but they actually do better than the rest of the components in your system. So I'm happy to see that Intel is actually paying a lot of attention to this and to the rest of the system and the platform as a whole these days, because clearly at some point the CPU becomes so efficient that any further improvements on that particular component actually don't help the platform as a whole sort of that much. So in concluding, it is definitely the case that we can't ignore the overall footprint of computing as a whole, and in that servers are a smaller piece of that whole pie, but is one that actually is growing relatively fast. One thing that we don't realize is how this whole trend towards server-side computing actually has a tremendous potential for increasing efficiencies in the way we deploy applications. And some kinds of applications probably can only be deployed in that model with any kind of efficiency. I will claim that we actually know how to design already very efficient data centers. We can do much better at that. But the key there, maybe it's less so sort of bleeding edge research at this point, is more sort of adoption of technology and practices that we already understand. We need sort of to refocus on just making the components themselves actually have better usage characteristics. And in that sense, energy proportionality is something that's particularly important for server class machines and will actually be very useful for low-end applications as well. I will stop here, and maybe we'll take questions afterwards, Fred? Or I could take a couple of questions now if you had. Thank you very much. It's a problem with abrupt finishes. You're not primed to ask your questions.
Can you hear me? Yeah, okay. I guess you didn't have a chance to talk too much about it here, but I know we've talked before about the sort of importance of making software and algorithms more efficient. And I was wondering if you might say something about, in your experience with, say, internet applications, what the potential is for sort of different models of, say, fine-grained parallelism or different kinds of computational methods
right.
in that area.
So there's one really important thing is that Justin mentioned, for example, how Intel is getting more performance these days, not by making CPUs with faster clocks, right? The megahertz are not really going up, but by giving sort of more cores or more CPUs inside the same die. The most important thing software can do in the short term is actually build software that can take advantage of that, and that's a non-trivial problem, so that's one of them. But by and large, a smart software engineer can make a big dent on efficiency, and that's something that when I talk to a computer science audience, I try to emphasize. I mean, if you looked at the remaining inefficiencies of data centers, right? If everybody builds sort of Google-like data centers that are wasting only 20% of every watt that's actually consumed, at that point, a moderately competent software engineer that makes their program run 30% faster, right, to some extent in the same hardware and the same energy budget, is actually beating sort of the entire mechanical engineering industry, if you will, to exaggerate the point, of course. So things like that, actually, focusing on optimizations, and it is actually still true that a lot of the things that software engineers can do to just make their programs run faster naturally will make them run more efficiently as well, with a few exceptions.
Hi, Luis. On April 1st, when you made a lot of this public,
Yes.
I know that there was an outpouring of thanks and appreciation from the rest of the industry, and I just wonder if you could talk about what's happened since then. I know it's only 7 weeks or something, but just talking about what has happened since then, because it generated a lot of buzz.
Let's see. I mean, one of the main things that I think that happened is that it raised the bar in a more explicit way. What we did on April 1st was more give people insight into how efficient we were. We had already been, for 6 months prior to that, been publishing our data center efficiency numbers. And what we noticed that happened was that they actually were so much lower than the rest of the industry that some people just decided not to believe us, which is perhaps not unreasonable. But also because we actually didn't give people much insight into how we did that, they were at a loss as to to what an extent what they could do in their facilities sort of today. And we showed a couple of things there that I think were very useful. One of them is that there are no magic bullets, right? This is the kind of problem where you actually have to work on 15, 20 different things in order to make a PUE of 2.0 to go down to sort of 1.2 or so. But if you actually focus on them, it does pay off. The other thing we showed was that even on facilities that we already had designed, there is opportunities for doing better in the way you run them over time. So we show graphs of our PUE over time, and just good management of the facility and good management of our computing resources. We showed facilities that started at 1.3 PUEs or so, that after a year and a half or so, were actually down to the 1.2, 1.18 sort of range. So I think the most important thing that had happened is that it raised the bar. And people actually could understand how we achieved the numbers we did. And sort of in that regard, I think it strengthened our message that we are doing this, this is how we are doing this. It can be done, and because it's being done not as a research prototype or a demonstration, this is our data center, it's our business, and we are a profitable business, thankfully. So it makes people believe that it's actually not inconsistent to be a profitable business in this area and run a very efficient computing infrastructure. Thank you. Thank you very much.
One thing I wanted to say up front is that there's actually a huge disparity in the energy consumption, the power consumption of the embedded devices compared with the data centers. And however, the position I actually would take is that some of the interesting trade-offs and in particular trade-offs between the power and the energy and the performance is actually quite interesting at at the particular scale that you look at. I've spent quite a lot of time working on sensors and embedded networks, or sensor networks, as you may know. And a lot of things that you do there is to make sure those devices are running as long as possible for months and years, since they are actually embedded in the physical environment, collecting data and do certain things. However, on the other hand, as you just heard from the earlier talk, the data centers with hundreds of thousands of machines, the power envelope is actually much bigger, and they typically actually consume something like 10 and 20 of megawatts, right, per data center. So you're actually talking about many orders of magnitude in the power difference. However, some of the trade-offs, which I'm going to actually talk to you about in the next few slides, are actually quite similar. In particular, there's the issue about if you try to actually put some of the components and the parts of your computing fabric into sleep, then how do you deal with the trade-off between the energy consumption and the responsiveness among other system performance metrics? And this is actually one of the device stack that we built in the embedded space. And this is a Lego-like modules. Basically, the idea is that you have these bricks, and these are actually very small. You can see that at the bottom there are 3 AA batteries. So that's the size you're talking about. You have different bricks. You have different processor bricks that they have very different power characteristics. Some of them are very small 60-bit processor, and some of them are ARM7. And you also have different radio bricks and also storage bricks. And the idea is that you can actually do these Lego-like, a mix and a match, configure a hardware stack for a particular problem. And also, there's a very interesting problem of the software. That is that given a particular application, how do you optimize across these components such that you actually get the optimal energy consumption while still meeting the application performance requirements, or the SLAs. And so, some of the things that we've been working on, and I get some really interesting results, is that how do you optimally map these different application and components into these hardware parts? And in particular, you have these different processors, different memory hierarchies, and the different states that these devices could be into. That is the power states, whether it's deep sleep, or it's actually a standby, or it's a high performance state. And you can do this at the design time when you're putting together software, or you can also do it dynamically at the runtime. Now, obviously, the complication is that often the time you actually don't know what the workload is going to look like. In this embedded space, you have these sensor data coming in, and you actually don't know how often those data are going to come in. When there's a fire alarm is going to go off, right? You actually don't have that prediction. So you need to be actually very dynamic and be able to adaptively put in those devices into the appropriate state so you can optimize for the energy use. Now, on the data center side, and you have a similar problem that arises from that. And this is a pretty typical data center in a conventional construction. And you actually have these floor, these are cooling vents, and you have the servers that actually takes the cool air, goes through the server, and pump out the hot air on the other side. So that's the typical, in many data centers, the construction. And the problem there is that many data centers are provisioned for the peak usage. And because the workload that these data centers serve actually fluctuates, because at night, people actually don't probably spend that much time querying and sending do the search or other things. And during the peak, you actually have many more user loads. So you actually have these diurnal, these workload patterns. And also on the facility side, you also have this distribution of the temperature, which sometimes they actually make this cooling very inefficient. In earlier talk, some of these modular container data center actually, in fact, is an excellent way of reducing some of those temperature gradient. And one of the things that we did in the last couple of years is actually have a research project called the data center genome. Just like a human genome, that we thought that a large facility like this ought to actually have all these characteristics where if you be able to map out, you can do a fair amount of optimizations with that. And at the core of this is basically to have lots of sensors that embed into data center. Some of them are hardware sensors, some of them are software sensors. The hardware sensors are the ones that actually embedded, around these machines that sense the temperatures, humidities, and as we know that if we don't have the visibility to where the hotspots are, then the cooling system, for example, would be quite inefficient because it tries to actually just cool down the hotspots to avoid the alarm. And you see some of those sensors that's shown there. In fact, we actually put together these sensor devices. One of the objectives is to make them very easy to install and a very low cost per unit. So I actually have one of those devices with me, and we actually had them manufactured about 10,000 of those. Once we designed this, it's pretty easy to send it to some shops in Shenzhen, China, and then you can get tens of those, 10,000 of those manufactured. So a lot of them are actually currently deployed across the Microsoft data centers to actually monitor the temperature and the humidity. Now, we also have sensors that monitor the other parts of the data center, and some of them are software sensors that are actually looking at the traffic over the network, looking at the machine states, and looking at the cooling systems and other things, and try to actually collectively try to figure out what the cooling system is doing. Is it responding to certain workloads in the data center, and how do we close the control loop to optimize for that? You saw one of the here, you saw some of those real-time mappings of the data center operations. This is the typical, so like the racks are arranged into these rows, and then there's multiple rows in this large data center room called the colos. And these are colors representing what's the power consumption, what's the workload, and what's the computer utilizations. And this actually gives the operators a very direct dashboard and visibility into how well your data center is running. And now, because of the embedded sensors that we have across those racks, in fact, you can actually do a real-time inspection of where the hotspots are. So this is in one of those hot aisle and the cold aisle construction, you have the cold aisle where the temperature is actually cooler compared with the hot aisle. You also can look at how the temperature actually distributed. Now, one thing that's interesting is that given that the temperature distribution and given the fact that these machines are all running workloads, and some of these workloads might be different from the other machines, can you actually optimize both the computing part as well as the cooling part so that you actually use the least amount of energy to cool that? So this is actually some of this very interesting work that we've been looking at. Now, let me actually give you a concrete example of some of the things we did with the software so that you can actually dramatically reduce the amount of power, and at the same time, without affecting the performance, right? I mean, it's always actually useful to think about, these machines are up to serve the particular needs. And if you want to reduce the power, and you also want to make sure that what's the impact that has on the performance of your internet services. So in this particular case, we actually look at a large internet service called the MSN Messenger. And the number of users at any given time log on to Messenger is actually quite large. We're talking about tens of millions of users, concurrent users that's actively using the services and maintaining a connection there. And the way that the Messenger works is that if a user actually wanted to log into a Messenger to talk to someone, it sends a request, and then there's a sort of a scheduler or dispatching unit, which basically says, given this particular unit, I'm going to pick a particular machine to serve this. So it's going to pick one of those machines called the connection servers or CS, and then that machine actually going to be dedicated to serve that. Well, actually, it's going to serve many other users as well, but this is the one that actually deemed to be the most appropriate at a given time. So you can actually see that in order to serve a particular communication purpose using MSN Messenger, actually quite a number of those devices is going to be used across the data center. You have these connection servers that's going to talk to the backend, looking at the credentials of the user, making sure this person actually is a legitimate users, and getting the list of his buddies or her buddies fetched from the address book. So all these things are concurrently happening in the background before a connection actually is established, and then you maintain that connection. Now, one thing to notice is that given those tens of millions of the users that's running on these machines, and if you look at the workload, and it's very interesting that even if you think about a worldwide workload, right? We're not just talking about U.S. We're talking about Korea. Also all sorts of these parts of the world, the user actually using the services, you actually see, this is actually we have lots of machines in the data center dedicated to this service, and they are partitioned into those clusters of 60 machines each. So let's look at one of the particular cluster. You actually look at these pretty interesting and repeatable load patterns. And this is about 1 day worth of 24 hours. So you can see Monday, Tuesday, Wednesday, and so on, right? And actually over the weekend, you see a little bit drop. So the question is really that, if you actually provision your data center resource for the peak, and then during the time of this trough, what are you going to do with those machines? One is to actually reprovision the machine for other services, or another way is actually perhaps to power down those machines or turn those machines into a very low power state. In the previous talk, Luis actually mentioned this excellent point is that if the machine is turned on but without serving anything, it still consumes a fair amount of energy. So what you like to do is to really power down or repurpose the resources for other uses. Now, this is actually pretty tricky to do, for several reasons. One is that if you want to actually repurpose the resources for other uses or power down the machine, and you have to actually figure out that how do you consolidate those workloads and then move some of those workloads to machines that need to be turned on, maintained. And the services we are talking about in this case is actually stateful. That is that it's not something you can shut down and instantly ramp up again. And they maintain a certain state where you somehow need to actually continue and onto some other machines. That's one of those challenges. The other is that even though you're looking at those patterns and you say, gosh, if I actually know exactly at any given time how many machines I use, I just allocate that amount of machine, I'm all set. But the real world is a lot more complicated. What if actually there's a news breakout, and all of a sudden there's a lot of users that come onto this messenger and tell friends about it. So you actually have some perturbations and things that you are not you cannot predict based on those histories. So what we really like to have is to be able to allocate just enough resources for the energy purpose, for performance purpose, but also leave some buffer just in case that lots of users come in and try to actually allocate the resources for such unpredictable purposes. So we're actually looking at a number of those techniques. I'm not going to go into details, but one way is to say, given the allocated number of machines for serving that load, and you can have one way to do this is to actually try to smooth the load across those machines, and this is typically called the load balance. And the other one is actually you try to skew the load towards the tail, the head part of those machines, serving just up to the capacity, and then leaving some of the tails that's available for the additional services. Now, one thing that I want to point out, you don't need to actually really read the axis, but just to actually give you what these axes represents. This is the power, how much energy it's going to use, and this is actually the performance hit. So that is that if you go to the right, that means that you got actually a lot more SIDS. SIDS is actually basically the server-initiated disconnection. That means further right, the worse the performance is. And that's the kind of Pareto curves that we are looking at. That is that you can either actually get a very energy efficient, but at one point we're actually going to get a lot of those server-initiated disconnection, or you can get very energy inefficient, but you actually have very, very good performance. And what you really like to find is actually on this curve, find a place, the knee, where you actually got a fair amount or majority of the energy saving without hitting the performance bottleneck. And so this is the study we did on the window, the MSN messenger. And one thing actually we discovered is that using this technique, you can just save up to about 33% of the energy without actually incur the additional performance penalty. So, one of my dream is really to actually putting some of those energy and the visibility into the energy use into the next version of Visual Studio. And as I said earlier, that software can play a really big role in improving the energy efficiency of all the IT equipment. And many developers in the world are actually using tools, Visual Studio, and there's a bunch of other tools to actually design and deploy the programs. And we often actually look at, for example, how fast the program runs and how much space it takes, right? These are the traditional way of thinking about the complexities of program. What I really like is to have a meter, like a JouleMeter, a very visual representation of how much your program is going to burn, how many joules are going to burn when you actually write your program. And furthermore, I want to expose some of those knobs to the program so that when they actually write a particular loop or do a particular construction of the program, it says that, gosh, this is actually less energy efficient. If you actually change the loop in a particular way, here's how much joules you're going to burn. So we actually picked the name JouleMeter as a project 2 years ago when we started this, is precisely to try to get a very fine granular visibilities into the program that you're writing, and also try to use the same set of techniques for runtime optimization. So if you think about it, right, you actually at one end, you have all these codes, and you have the different workloads that these programs are going to serve. And what JouleMeter does is that it takes the test workload, and it actually generates a detailed profile in terms of how much energy consumed by each of the hardware components, and also the software activities that's being executed on those components. The kind of thing you could do with those is, one is actually to do the kind of things such as, the compiler could actually be a little smarter about, what these different consequences are, and try to actually optimize for that. The runtime could actually use that to scheduling and give a policy which can trade, for example, the quality of the services with the energy. And we actually had developed a number of models for different machines. And the core idea is the following, that if you be able to actually gather these events and counters, and then you should be able to build a model and mapping from those events to the power consumptions of these different components. And there are actually well understood modeling techniques that allows you to build a very robust models for that. And of course, the proof of the pudding is to actually see how well these techniques works. And just to give you a sense that, this is actually shows over time, the different, the energy profiles of the energy profile using the models, as well as actually the ground truthing. And here is actually a breakdown of the different components over that period, executing a particular set of applications, the CPUs, the memory, the disks, and how they actually, the power varies over time. Now, of course, the really interesting part is that if you have multiple things that are running on a set of machines, and what you really like to tease out is that, which application you're using, which, how much energy, and which components are being stressed. And this is actually typically actually a very useful thing to understand if you want to allocate those things and consolidate onto these virtual machines. So to conclude, what I think is really exciting, when we think about the energy efficiency and the software techniques, is that the opportunities actually exist at many different levels, right? You're talking about the hardware part, but at the system levels, at the application levels. The key is really to expose many of those optimization knobs, and also give people the visibility that if you actually tune some of those knobs, what consequences are you going to see? One thing I'm actually really a strong believer of this is that we ought to actually think about energy as a first-class citizen, and think about energy complexity in design systems, in particular design a computing system. As I mentioned earlier, that in addition to think about the algorithmic complexity, such as space and time, we ought to think about what's the energy, the footprint, and what's the trade-off of energy and performance when you write a piece of code. And I think this is likely to be one of those things that computer science ought to actually look at in the next decade. With that, I'll be happy to take questions.